In scenarios of supervised learning where discrete variable is the output, we are far more lucky because we have very strong measures of evaluation of the corresponding supervised learning. So, within supervised learning, we have classification as the case where we have discrete output variable. So when you say discrete output variable, you typically have some input variables and some definite possible output variables. Let's take the simplest example of, say, binary classification, where the potential output variable is either a true or a false. So there are several examples where binary classification itself is a powerful modeling tool. For example, you can detect something as a spam or a non-spam, or you can have something like you want to provide insurance or not provide, or you want to calculate something as risky or non-risky, or you want to classify a potential tweet as positive or negative. So there are several scenarios where classification itself provides a very powerful mechanism for modeling the corresponding problem. In all of such cases, we have a very powerful set of evaluation metrics because of the rigid and formal nature of such problem formulations. In such cases, there is a tendency that we will take the entire input data, feed it to our algorithm, and generate a corresponding classifier which can be used for classification of any new input data that comes in, and you can probably classify it as a spam, non-spam, etc. But the problem with such an approach where you take the entire input data as the source of input for your classifier is that it is highly biased towards your input data. It is possible that it has less predictive power for future data which may not conform to the distributions of the input data which was fed into it. So because of this nature, we lose on the general realizability of the classifier which we have learned for future scenarios. And due to this, and the fact that we have a rich labeled input data present with us, we actually can do an interesting trick in order for us to help evaluate a classifier. The corresponding technique is called splitting the data into training and test sets. The way it works is you take the input data and then you kind of split it into two data sets. Training set, test set, randomly, depending upon some percentage split. Let's say 80%. 80% of the data becomes training and 20% of the data becomes test set. And this is done randomly without replacement, so that you have two distinct set of data items. One is training set and another as test set. Now, on the training set is where you run your machine learning classification algorithm. And then you get your corresponding classifier model. Once you get your classifier model, that becomes your machine learning model, which is useful for classification of future data. Why do you wait for new future data? We already have set some part of the data aside for test set which you have not used. And that's the trick of the trick. What you do is now you treat this test set as potentially new data that is coming your way, and now you apply that onto, you apply the classifier which you have learned onto this test set on the input of it, and you get some predicted class, right? Based on classifier applied on input of the test set, you get a predicted class. Now, predicted class is something which is the potential output class as determined by the classifier you have learned from your training set. But you already have labeled output in your test set, which is the class values for your output variable from the original data itself. Now you have predicted class, so this size is again 20% data, right? So now what you can do is you can match the two and come up with a notion of accuracy. Means what is the percentage of correctly predicted class by total test set size, right? So for example, suppose you had 20 instances and you predicted 16 of them correctly, where predicted class is same as the original labeled output. So your accuracy becomes 16 out of 20, which is 80%. Same thing, suppose you have something like 19 out of 20, then you have a 95% accuracy of the model. So you see, the beauty of this is you try to look at the overall model effectiveness within the original data given to you. You don't have to wait for new data to come in. So this way of using the data itself to validate the model gives us a lever to iterate. If accuracy is not good, you can go back and revisit the algorithm and try the algorithm differently with different parameters, hyperparameters, etc. Run it again till you're satisfied of a certain accuracy level. So what we have in supervised learning is a great approach by which we can use the input labeled dataset itself to label the corresponding accuracy and use that to iterate our models till you get sufficient accuracy.